All right, we're going to be looking at day 1 of our notes on functions and continuity. So today we're just going to look at if we can determine the continuity of functions. And first off, we got to look at what is a function. Well, a function is any type of special relationship in which every input has only one output. That is the most important part. That's why it's in bold there. Every input has only one output. So on this mapping, where we have these bubbles here, set A and set B, we are going to look at set A, make sure that every unit in set A has only one arrow coming from it. So because the little a maps to a 1, the little b maps to a 2, and the little c maps to a 3, it doesn't matter that nothing maps to a 4. All that matters is that each letter only has one arrow coming from it. So that is a function. If you look at the second set here where it says not a function, there's 2 arrows coming from that b. So that's why it's not a function, because the b maps to both a 2 and a 3. It's not predictable. It's not useful. So let's look at some examples here. The number 1 maps to a letter D, the number 2 maps to a letter B, the number 3 maps to a letter A. All right? Because there is only one arrow coming from each of the x's, it is a function. That is a function. All right, let's look at this middle one here. If we look at the input column, there's a 3, a 4, a 5, a 4, and a 10. You notice the 4 is repeated. So you gotta be careful here. Now, since this 4 maps to a 7, if that second 4 had mapped to a 7, it would still be a function because they are the same outputs. But because this is a different output, it's a 14, therefore it is not a function, no function. Then let's look at example C here. We have a 1 mapping to a D, a 2 mapping to a B, a 3 mapping to a C, and a 4 also mapping to a C. Now, these are the ones that usually trip students up because you see 2 arrows and you think, oh, it's 2 arrows, so therefore it's not a function. However, the 2 arrows are pointing to the same unit in the Y section. They're not coming from the same unit in the X section. So only look at the X section to determine if it's a function or not. And since there are no parts of the X that are mapped to 2 different Ys, it is a function. So that is a function. Now, when we look at a graph, there's an easy way to tell if something is a vertical line or not. All right? And the simple way to tell that, if it's a function or not, and the simple way to tell that is the vertical line test. So the vertical line test. So if you look at example 2 here, we're going to determine if the following graphs are functions. So if you look at this first graph, this looks like a linear equation. All right, it has a slope and it's a straight line. There's no curves or anything. We're going to put our pencil, our ruler, or edge of a paper right there on the left side of the graph, and we're going to move that straight up in a straight up and down motion to the right. So we're going to keep it vertical. In other words, our pencil is going to stay vertical, and we're going to move that to the right. And as it goes across, it's going to touch this red line in different spots, but it's never going to touch more than once at the same time. So because of that, it passes the vertical line test, and therefore it is a function. So we're going to do that again with this parabola, this upward opening parabola here in the middle. And as it moves from left to right, it touches this graph in lots of places, but never more than once at a time. So therefore, yes, that is a function because it passes the vertical line test. Now, as we move on to this third one, this right opening parabola, you'll notice that as I move my pencil from left to right, at -5 it only touches once, but as you move from left to right, it starts to touch in more than one spot at the same time with the same x value. So therefore, it does not pass the vertical line test, and it is not a function. Now, a parent function is a function type without any manipulation, such as translations or dilations. And the key features of these functions We have x-intercepts, y-intercepts, maximum and minimum points, domains, ranges, and end behaviors. So we're going to look at all of those key features eventually. But a linear function, the parent function of a linear function is f of x equals x. All right, so that has a slope of 0 and a y, or a slope of 1 and a y-intercept of 0. So, therefore, it's going to go like this. All right, and it's going to just go through that 0 point, and it's going to have a slope of 1. Now, the quadratic function, parent function, is f of x equals x squared. All right. Now that parent function goes through the point 0, 0, goes through the point 1, 1, and negative 1, 1, and then it goes through the point 2, comma 4, because 2 squared is 4, and negative 2 squared is 4. And so that's going to look like that, a parabola. Next we have an absolute value function. Absolute value function is going to combine those first two. In this, the function is f of x equals the absolute value of x. Remember, absolute value is just the distance from 0. So it has an x and a y-intercept of 0, 0. And then it's going to look a lot like the linear function, parent function, on the right side. And it's going to be in reverse of that on the left side. And it's going to kind of look like a parabola too, because it opens up like that and has a v. A cubic function is f of x equals x cubed, because x is cubed. And that has a little curly Q in the middle here. I don't know the official term for that, but it kind of makes an S shape there in the middle. A reciprocal function is the graph of f of x equals 1 over x. And it has a pretty weird shape because it's going to actually have two different parts to it. It's going to look a lot like this. And we call that, it has a vertical and a horizontal asymptote. Now be careful how you say that. But that is our reciprocal function, and we'll get to that later on this year. An exponential function, f of x, is equal to some number to the x power. All right, so we say that's f of x equals b to the x power. All right, and so whatever x is, obviously, as x is negative, it's going to be a fraction, and as x is 1, anything to the, or as x is 0, anything to the first power is 0, and then it's going to just get big fast over here in this direction. So it's going to look like that. Logarithmic function is f of x equals log base b, so what's some base of x, and the graph of that is going to look, it's going to look a little bit weird again. It's going to look like that. And then we got the square root function, f of x equals the square root of x. Well, obviously, we can't take the square root of a negative number. That is imaginary. So the biggest number we can take the square root of is 0. So we're going to start there at 0. The square root of 0 is 0. Square root of 1 is 1. Square root of 2 and 3 are some decimal. And then we have the square root of 4 is 2. So 1, 2, 3, 4 is 2. So it's going to look like that. So As we go along, example 4, is it a parent function? Well, the big thing to know, first of all, is that this is a linear, but its y-intercept is not at 0, 0. You'll notice its y-intercept is down here. So therefore, it is not a parent function. For B here, you have a parabola. The parabola, if you look at the parent function on our notes, the parabola's parent function has a y-intercept at 0, 0. This one has a vertex here at 4, negative 4. So therefore, no, that is not a parent function. And then letter C here, absolute value function, it does have a vertex at 0, 0, so that is the parent function. And it looks like it has a slope of 1. That's the other thing to check, that the slope is 1. So that is a parent function. All right, last part here, discrete and continuous functions. Continuous functions can be graphed with an unbroken line or a curve. That means you don't have to pick your pencil up as you're drawing it, if you're good. Discontinuous functions are functions that are not continuous curves. And then a discrete function is a discontinuous function made up of unconnected points. So when you look at the graph of a discrete function, it's just going to be a bunch of points. They're not going to be connected by any lines or anything like that. It's just points on a graph. So the difference between a discontinuous function and a discrete function is a discontinuous function does have some lines connecting the points, maybe several different point-to-point lines, or there may just be a couple, but a discrete function is just points, no lines at all. So if you look at the examples here, example A, just a bunch of points here in a horizontal line. This is going to be a discrete function. If you look at example B, it is a upside down parabola, but it looks like if you were to put your pencil at one end, you could go all the way up and then back down and never have to pick your pencil up. So because of that, this is continuous. And this third one, C, it looks like you can go from point to point, there's a line, then there's a gap, so you had to pick your pencil up, and then there's like this upward sloping line. So because of that, I had to pick my pencil up, but there are lines, so this is discontinuous. Now, on our homework, there are some questions like this. And what they're going to ask is, it won't ask if it is discontinuous. It's going to ask, is it continuous or is it discrete or is it neither? All right, so obviously if it's not continuous, so it's not like you can just drag your pencil from one end to the other, and it's not discrete, it's not just a bunch of individual points, it's something kind of in between. Well, we normally call it discontinuous. On our homework, you're going to say it's neither discrete nor continuous. So that's how you answer that question. All right, hope that is helpful. If you have any questions, come and see me.